Hey mathematicians, here are your notes for functions day 2. So functions have a special place in mathematicians' hearts. In fact, Leonhard Euler, that is how that name is said, loved them so much that he gave them a special notation. And I know this is really hard to read, but it says if y is a function of x, let's use f of x, and I'm going to write that so you can see it a little bit better. F of x. We're going to use f of x for y. Well, what does that mean? F of x is not f times x. What you see here, actually I should highlight that, basically says that f of x is now going to replace y. And the reason for this is that it gives us a little bit more information. So when I give you a final solution to this problem on the right, I'm going to get y equals, let's say we end up getting 0 as our solution. This piece of information is all I have for my next problem. However, when I use the f of x notation, what this allows me to see, say I plugged in -3 and it kicked out 0, y is the same thing as f of x, but this gives me 2 pieces of information while this only gives me 1. This gives me an x coordinate that I plugged in and a y coordinate that I got out, while this only gives me a y result. So let's look at that a little more. A function works like a machine, as shown in this diagram. A function is given a name that can be a letter such as f or g. That's what you saw above. The notation f of x represents the output when x is processed by the machine. So some of you may remember doing tables when you were in elementary school where you put a number in and you get a number out. Functions are very much like that. Note, f parenthesis x parenthesis is read f of x. When x is put into the machine, f of x, the value of a function for a specific x value, comes out. So, numbers are put into the function machine, as is the case to the right, for f of x equals x squared minus 1, one at a time, and then the function performs the operation on each input to determine the output. For example, when x equals 3 is put into this machine, into this function specifically, the function squares it and then subtracts 1 to get the output, which is 8. The notation f of 3 equals 8 shows that the function named f, shown in here, connects the input 3 with the output 8. So that's a lot. That's a lot of reading, and let's put that into a little bit of actual context. So find the output for f of x equals x squared minus 1 when the input is x equals 4. So that is find f of 4. Basically, what you'll notice in this one is that if you have an x on the left and an x on the right, they match really nicely. But notice when we replace x with 4, that is what we're going to do in the function as well. So anywhere that I used to see x, I'm now going to put the number 4. That is me inputting a number into the function and solving to get a number out. 4 squared is 16. 16 minus 1 is 15. So f of 4 is 15. And as I was saying up above, if I had just solved for y in this case, I'd get y equals 15 and never know what I started out with. This allows me to know what I started out with. Next up, what would you calculate f of 1 to be? What about f of negative 1? We're going to do the same thing. Instead of f of 4, we're going to plug 1 into our machine. 1 squared minus 1 equals 0. There's our answer for f of 1. What about f of negative 1? We still plug in f of negative 1. This is in parentheses. Negative 1 squared is 1. 1 minus 1 is 0. Notice that when I'm solving these problems, I'm not doing anything with the number on the left. I'm not dividing because this doesn't say f times negative 1. This says f of negative 1. So when I get my answer, I don't go back and divide by negative 1. I don't add negative 1. I don't do anything. This is information, not computation. So, based on the function shown to the right, calculate the following values. Again, I know this is really hard to see. I'm sorry. Our printer has been struggling. So, that is 6 divided by the sum of x minus 3. So, f of 0. If I go ahead and plug in f of 0, that means that anywhere I see an x in my function, I'm going to replace it with 0. Therefore, I get 6 divided by 0 minus 3. This becomes negative 3 on the bottom, and 6 divided by negative 3 is negative 2, just like that. Same thing with f of negative 3. I'm going to plug it into my left, plug it into the right. I get 6 divided by negative 6, or negative 1. If you feel like you know what's going on, go ahead and try those next two with f of 2 and f of 3. If not, we're going to go through them together. If you do choose to pause, you can still come on back and watch them afterwards. All right, f of 2. I always like rewriting just so everything's on the same line. You don't have to if you don't want. 6 over 2 minus 3, that would be negative 1 on the bottom. 6 divided by negative 1 is negative 6. And last but not least, f of 3 equals 6 over 3 minus 3. 3 minus 3 is 0, which means we get 6 divided by 0. And as I have said before, maybe in this class, maybe in my other classes, when we divide by 0, the universe implodes. It does not work. We cannot divide by 0. It breaks the laws of math. So we actually do not have a solution for the final problem. That's okay. We just write no solution. Let's go ahead and flip to the back and keep going with the same idea. So composite functions, sometimes the outputs of one machine becomes the input of another. These are what are called composite functions. So for example, f of x, our first function, is equal to 3x plus 1, and g of x is equal to 2x plus 4. So you've got f of x up here, you got g of x down here. It says, what would you get if you fed x minus 1 into the first function? Well, let's do that. F of negative 1 equals, I have 3x plus 1, so anywhere I see an x, I'm going to replace it with negative 1, equals, so 3 times negative 1 is negative 3, negative 3 plus 1 is negative 2, just like that. Now what happens if you feed the output of the f function, that's what we just got, this is the output, into the g function? So if we plug that in here, meaning if we say g of my output, which was negative 2, plug it in so it's 2, negative 2 plus 4 equals, so this would be negative 4 plus 4, or 0. So step 2 is shown right here. This solution is written as g of f of negative 1. And what this says when we use a composite function is that, much like parentheses, we're going to evaluate the inside first and then evaluate the outside. So notice we plugged in negative 1 to our f function, and then we took that output and we plugged it into our g function. So there are 2 steps involved here. So let's see that again with 2 more examples. If I have g of f of 0, I'm going to start by calculating the inside so that I can replace it. F of 0, I'm going to use the same function here, 3x plus 1, to get 1. That is my f of 0. And if f of 0 is equal to 1, there's no reason I shouldn't be able to take 0 and replace 1 and replace that f of 0. So g of 1, it was f of 0, now it's 1, equals 2, 1 plus 4, and my final answer is 6. If you want to write your answer without all of the work, I often say write g of f of 0 equals 6, and then circle that. I'm not going to do it for the sake of space right here, but you can see what that would look like. Now, I might not give you the machines in order. I may just give you two functions right next to each other and say you have to do them in a different order. So let's do g of 5 and then do f of g of 5. Okay, g of 5, let's do that inside one first. 2 times 5 plus 4 is 14. Then I'm going to do f of 14. Remember, I'm replacing g of 5 with 14. That would be 3 times 14 plus 1. When I calculate, I get 43. And that is my final answer. All right, last up is interpreting a function graph. This is one of my favorite parts, but I know it can be tricky, so just follow along. The distance d of t, notice we don't always have to use f or g or x, represents the distance d, Gulliver is from home t hours into his trip. So each of those letters represent something. Keep that in mind. Use the graph to evaluate the function at each value. At d of 2. Well, remember from our previous page that the number inside of the function notation is our x value, and whatever it equals is our y value. So what this is asking me to do is go over to my graph and say, at 2 in my x, what is my y value? Well, at d of 2, I actually did this wrong. It's not even. That's actually my d of 2 value. When I go straight up on the graph, my y is actually 4. Okay, let's see another one. When my time is 5 hours into my trip, time is over here, distance is over here. When my time is 5 hours, my distance is 11 miles. Okay, d of 2.5, that means when I am 2.5 hours into my trip, right here, my distance is 4 miles. Go ahead and see if you can do that last one on your own. All right, at time 10, we are how many miles from home? We are 0 because that is our y value. Notice it gives you an x, it asks for a y. Now we're going to calculate the value of t that makes the equation true. So when d of t is 2, what is t? So this time instead we're looking at the distance, meaning we're looking at the y-axis. So when our distance is 2 miles, what is our time? Well, this one's a little tricky because if we actually draw a line across here, you'll notice we have, that's a sideways line. Haha, there we go. You'll notice we actually hit at 2 different points on the graph. So when we are 1 hour into our trip, we're 2 miles from home. But when we are at 9 1/3, I would say, hours into our trip, we are also 2 miles from home. Notice this is still a function because remember, your y value can repeat as long as your x value doesn't. These are technically x values. All right, try that next one on your own if you're confident. Go ahead and pause the video. All right, notice our distance is 5 miles. So I'm going to go ahead and put my little line across here. And I notice that at time 4, I'm 5 miles from home. And also at time 8.5. We'll just eyeball it. So, x value, y value. Last one, write the rule. Based on the given inputs and outputs, can you fill in the blanks? After you fill in the blanks, can you write the rule of the function? Notice we've got a 1-to-1 going on, we've got a 49-to-7, and we've got a 25-to-5. Well, it looks like there is a relationship between these, and I will actually go ahead and tell you that there is. I want you to pause the video here and see if you can find out what that relation is by yourself, and then come on back and we'll talk about it. All right. Hopefully you had a chance to pause and think about that yourself. Right off the bat, I notice that the square root of 49 is 7, and the square root of 25 is 5. That also holds for my 1. The square root of 1 is 1. So I go through and I check and I say, well, the square root of 9 is 3, and the square root of 100 is 10. And as I go through, I notice it works for most of these. 2. This one is a little tricky because it gives me the f of x, but because I'm taking the square root in this direction, in order to go the other way, I just have to square it. So I get 16. Square root of 0 is still 0, and the only tricky one is this last one right here, because if we take the square root of 20, we actually don't get a nice number. But that's okay, we can just write it as the square root. So in this case, our function, when our input is x, to get to our output, we take the square root of whatever our input was. This is how functions work. We're not quite done yet. We have one more day tomorrow, but if you have any questions before then, don't hesitate to let me know.